Ladies and gentlemen, we have a bit of a dilemma on our hands here because throughout this lecture, thanks by the way, that was amazing. I have, by my rough estimate, about 1 million questions. Now I think that there are about 300, 350 of you out there right now, and I'm assuming we don't have the same questions in mind, you have probably 1 million of your own. So by that tally, we have about 350 million questions for you right now. Okay. Now, it's unlikely we'll get through all of them, but he has graciously offered to answer a few. So with that as an opening gambit, does anyone have any questions for Professor Schmidt?
The interesting thing on this front is that we've just started our first massively open online course where we have 17,800 people asking questions. And with technology, you'd be surprised of how well you can do, because fortunately the audience answers their own questions for you, which is very useful as long as they get the right answer. Maybe we should bring the house lights up so we can see the audience. Thanks.
If the universe is expanding and so more and more dark energy is being created, how is energy conserved?
How is energy conserved? So I can give you two answers. The first of all is the one audience gasp. Within cosmology, it turns out energy is not necessarily conserved in the way you are taught. That being said, general relativity has its own accounting system. So imagine dark energy is being created. It has what we say negative pressure. The negative pressure is what causes the universe to speed up. Now, the speeding up of the expansion of the universe you might think is positive energy, but it's actually negative energy. And so the dark energy that's created is offset in the ledger by the expansion of space. This acceleration of space is an energy sink. And so they effectively offset each other. And so everything has an accounting. Sometimes it's not very intuitive. If you know physics, we have a way of describing work as being pressure by the times the change of volume. Since the pressure is negative, change of volume is positive, the energy is negative.
Hello. Thank you for that amazing speech, by the way. Can you comment on the latest thinking on the first cause for the universe and how something could come from nothing, so to speak? This question is, of course, of interest to people following the ongoing debate between skeptics and theists.
Yep. So I'm what they describe as or I self-described as a militant atheist, which is I don't actually have a very strong opinion on this. So imagine a universe from nothing. Well, it is possible within an energy conservation sense to essentially have the universe we have be born out of essentially a quantum fluctuation from nothing. Fine. But that quantum fluctuation still had to occur in something where physics as we know it exists. So what created that? Don't know. So I can always take the creation of the universe to a point where I am not going to be able to describe it, I would contend, with physics as we know it. So I believe that there are limits to knowledge. I don't know what the Big Bang was. I don't know what came before the Big Bang. I don't know what created our universe. There are limits to knowledge. We can think about it, but that is ultimately a metaphysical question, which I'm happy to say I don't know.
Hi. Hello? Hello?
Yep.
Hi. Yes, thank you for that wonderful lecture. I was actually just curious about your personal opinion about something. So my understanding is that dark energy is quite a widely accepted model now, and it's strongly inferred from the best data that we have available. How confident are you in your own mind that that's the correct model versus something that's perhaps a little bit more exotic and unknown as yet?
So I have, again, almost no opinion. I suspect that whatever, the evidence right now is whatever is causing the acceleration is something very close to Einstein's version. But the ultimate question is that dark energy going to stay the same through the eternity of time, or is it going to change in the future? We very strongly suspect right after the Big Bang, the universe accelerated like it is doing right now, but fortunately stopped. And that's what allows all of us to be here in our universe. It seems to be doing that again now. Is our current expansion going to stop? Or is it frozen in forever into time? That's the big question. And I'm an evidence guy. There's no evidence one way or the other. I don't know. And it may end up being almost impossible to figure out because predicting the future requires infinite understanding of everything. And we'll never have that. And if we do, we won't realize we do.
Thank you for this amazing talk. My question is, will we ever know what's beyond the horizon event of black holes?
Beyond inside the horizon? Well, there is a theorem that says you cannot possibly know. That is, once you're on one side of a black hole and something's on the other side, the only thing that comes out is radiation can come out in the form of what we call Hawking radiation, which is what people were looking for when they invented Wi-Fi and didn't discover, but no information will come out. So that would say pretty solidly, no. Once you're on that side, you're gone, and nothing. You will never know about that side. And I don't think that's likely to change. I think that's a pretty fundamental part of the universe we live in.
I don't know if I'm right next, but just a question, like the universe is infinite, but was it always so, even at the Big Bang?
It is very difficult to turn finite into infinite unless you have an infinite amount of time. So if the universe was finite at the time of the Big Bang, it's certainly finite now. It may eventually be infinite in infinite time in the future. If the universe is infinite now, the converse is it was infinite at the time of the Big Bang. And so while our part of the universe we see right now, we can run back to a time when the universe was the size of a football. If the universe is infinite now, that means the universe was infinite then, and there's all these bigger and bigger spheres around us, which we can't see, but existed at the time of the Big Bang outside of essentially this horizon where information can reach us. A singularity does not mean, so a singularity is very complicated. And so singularity means we don't understand. And so I can run the universe back to a tiny size of a football, but at that point, gravity and quantum mechanics as we know it break down. We can't even guess what happens. So when people say the universe started in the singularity, they're extrapolating to a place I am not prepared to go. So I don't know what happens at singularity because my physics, even my tiniest bits of intuition, go away. So I'm willing to take it back to that time, the size of a football, but no further. Yes?
Fantastic lecture again. With your research, you were talking about how you had to link all the computers and everything's crazily bad compared to today. The expansion of technology, where do you think the best improvements would suit for better astronomy, like bigger telescopes, closer range of finding a better cosmic microwave background?
So ultimately, astronomy is driven by the technology, and choosing, bigger, better telescopes are going to be really important. But there is a boundary condition, and those boundary condition is money. So big telescopes are really expensive. Astronomy is a frontier subject, which means our aspirations are entirely limited, more or less, by the effort we put in. There's still a lot to learn. And so it's a very complex question is, what should we be doing? Because I actually have to weigh the cost and what society is willing to pay versus the amount of knowledge we get. And we've invented Wi-Fi, great. I don't know what we're going to invent next. It's very expensive. And so I can't actually tell you. I think right now we're building a next generation of very large telescopes. We're developing telescopes that survey to a shallower level the entire sky. I think those are very smart things to do. Cosmic microwave background work is no longer going to be in space. I think it's almost entirely going to be on the ground now because of the way we do technology. And I think that, like everything in basic research, the broader spectrum of things you play around with, the better off you're going to be, because there's just so much we don't know. Yep.
Me again. I have a question about your current work. So I know that you're the leader of the Skymapper project, and I was wondering how is that actually going to map dark matter? Because I know that's one of its goals.
Dark matter and dark energy. So the Skymapper project is this quite small telescope that's located at Cunnabarabran. It has a 268 million pixel CCD camera, about that big by that big, which costs $2.5 million, so it's not cheap. And it is in the process, probably if it wasn't raining last night, I haven't looked at the weather yet, took images of probably 100 full moons worth last night. So over the course of 5 years, it will have imaged every part of the southern sky many, many times. So through that, we can do a census of the universe, of what's out there. We will have essentially measured the basic properties of every star and galaxy visible to some brightness level. We will actually know a fair bit about a lot of those stars. We can identify the needles in the haystack, because this telescope has very specific filters that allow us to observe the colors of the stars and, for example, find stars that have almost no metals in them. Why are they interesting? Because they were created right after the Big Bang. The Big Bang made hydrogen and helium, pretty much nothing else. And so if we find a star that has, for example, no iron in it, it hasn't been polluted by any supernovae, and we know it's one of the first stars. And indeed, our team found earlier in the year the most primitive star ever detected, and that's one of the links to the Big Bang to the current universe. We can also pick, it turns out, stars that were thrown out of the middle of our galaxy, because our middle of our galaxy has a supermassive black hole, about 3 or 4 million times the mass of our sun. And if you have stars that are in binaries that come sweeping in, they come in, and the tidal effects, where the black hole pulls harder on this side than on that side, can break those binaries out and throw the stars out of the middle of the galaxy. So occasionally, you will find these stars zooming out of the galaxy. They're on nice, what we call like a ballistic orbit. They're like taking a howitzer and shooting it up. And it turns out that means you don't have to worry about them which direction they're moving. You know which way they're going. That allows us to go through and calculate, if we get several hundred of these, how the dark matter is distributed in our galaxy. And that's something we've never directly been able to do, because you've got a mess of things you have to deal with. So that's one way we're going to look at dark matter with that.
We have time for one more question.
Last one.
Right.
So when you were talking about the acceleration and how eventually that would get to a point where you couldn't see things that were far enough away, so that sort of creates a bit of an event horizon, like
Yes.
within our universe of things we can see and things we can't.
Yes, and so the interesting thing is there certainly is a horizon. There's a horizon right now, it's 13.8 billion years, and we can't see anything further than that. So in the future, when I showed you that really deep picture with the Hubble Space Telescope of those galaxies, the light that they emit right now, 13.8 billion years after the Big Bang, will never reach us because the space is expanding too quickly. So what happens? Are those galaxies suddenly going to blink out? No. Over time, their redshift increases faster and faster and faster. And that causes time dilation, which means that if I were to see a clock, their clock would become slower and slower. So eventually, as these things fade away so that we never ever detect another photon, their clock stops at maybe 2.5 billion years after the Big Bang. And that's when they go outside of a horizon. So they never formally disappear, but they become infinitely faint and their clock stops. So you will essentially, if you had a sky of clocks, depending on how far away they are right now, they would all eventually in the future turn off at a given time.
Could I follow that up with just another quick one?
Okay. And that should have really bent people's minds what I just talked about, because it's
Yeah.
hard. Yeah.
So I guess basically, how long would it take for this sort of effect to actually affect the observations you want to take and, affect us being able to do cosmology? And sort of in the far future, when we can't see those things, would people in the far future be able to even know that cosmology sort of exists? And,
So I think the evidence is no. In the future, you won't literally be able to do cosmology as we know it. Just to be clear, this part of the universe is not expanding. Gravity here collapsed this part of the universe, and so our own galaxy will be preserved for trillions of years into the future. But right now, what we think we can do with the next generation of telescopes is just barely see the stretching of light happen in real time. The next generation of telescopes will actually be able to look at galaxies and see their redshift increasing. If we were to come back to Earth, well, I wouldn't come back to Earth. Let's say we go by to a nearby M dwarf star, a little star that's got a lifetime much longer than the 5 or 6 billion years we have left here in our own sun. We were to come back 100 billion years from now, then the nearest galaxies that we can see today will be almost at the distance of the most distant galaxies we can see right now. So the universe by then will effectively be empty. If we were growing up and on this, at that time as a new civilization, we would go out and we would see this abyss beyond our own galaxy. We would build a couple generations of new telescopes, and we would say, gosh, there's nothing to see. Okay, let's do something else. So there would be a couple little hints 100 billion years from now, which if you were smart enough to build the Hubble Space Telescope and look at the entire sky, you might be able to see. But then if you wait 200 billion years, then there will be nothing that we could see now visible to us, and essentially the universe is empty. A good place to, a good existential place to stop.
Ladies and gentlemen, please join me in thanking Professor Schmidt for what was an amazing. Thank you so much.